Okay, the next one is radiation. Radiation is a little bit difficult, but we will only cover a simple part in this chapter. Radiation is the energy emitted by matter in the form of electromagnetic waves or photons as a result of changes in the electronic configurations of the atoms or molecules. The difference between conduction and convection and radiation is that radiation does not require the presence of an intervening medium. So radiation doesn't require a medium. In vacuum, you have radiation. You don't have conduction or convection in vacuum or in the space, but you have radiation. The solar heat comes to Earth by radiation, for example, solar energy. And all bodies at a temperature more than 0 emit thermal radiation. When the temperature of a body is more than 0 Kelvin, that means it emits thermal radiation. Okay, so the maximum rate of radiation emitted from a surface is given by this equation. Sigma AS Ts to the power of 4. This equation is called Stefan-Boltzmann law. And here AS is the surface area, Ts is the surface temperature. What's the unit of surface temperature here? What is the unit of surface temperature? Kelvin. Is degree Celsius okay? Is degree Celsius okay? No. Okay, thank you for your answers. It's correct. It's correct. And sigma here is called Stefan-Boltzmann constant. It is equal to 5.67 times 10 to the minus 8 watt per meter square Kelvin to the power of 4. And which bodies emit this maximum rate of radiation? Black body. The ideal surface that emits radiation at the maximum rate is called the black body. Actual bodies are not black body, and radiation emitted from real actual surfaces is given by this equation. The same equation here, we multiply by epsilon. Here epsilon is emissivity, and it is a measure of how closely a surface approximates a black body for which this. So epsilon is between 0 and 1. Okay. This question is for Oğuzhan Kılıç. Oğuzhan, what is emissivity of a black body? Oğuzhan, emissivity of a black body. Oğuzhan doesn't know. Okay, let me ask this question to Kürşat Berkay. What is your answer? Kürşat, 0.5. Okay. Let me ask this question to Bahri Olgay. Bahri, what is your answer? Bahri Olgay. Okay, the answer is 1. For a black body is an ideal surface, its emissivity is 1 because it emits the maximum rate of radiation. Epsilon is equal to 1 for a black body. For actual surfaces, it is less than 1. So emissivities of some materials are given here. As you can see, aluminum foil has a very low emissivity. Some other materials have high emissivity values. Polished metals have low emissivity values, but normal other materials have high emissivity value, like human skin, wood, soil, water, they have high emissivity values. Here, for example, it's a black body. What is the rate of radiation emitted from this body? The equation is this per unit area, sigma Ts to the power of 4. Surface temperature is 400 Kelvin. The area is not given, so we determine the result per unit area. Emissivity is equal to 1 because it is a black body. So when you use this equation, then you obtain this result. Or this equation because it's a black body. Stefan-Boltzmann law. Okay. This question is for Emircan. Emircan, what is the name of the equation in conduction? Here in radiation, it is Stefan-Boltzmann law. In conduction, what was the name of the main equation? Emircan? Emircan, are you there? Fourier's law of heat conduction. Okay, this question is for Önder Kara. Önder, what is the name of the equation for convection? What is the name of the equation in convection? Convection equation. Önder, what is it? Önder, are you there? Okay. Önder Kara. Do we have a student named Önder Kara in our class? Önder, are you in my class? Are you sure? Because I don't remember your name. Önder Kara. It doesn't look really familiar. Are you in the second year or the third year student? Önder. Third year. You are not a new student, right? Because I don't remember your name. Third year. Okay. Maybe I forgot your name. Okay. Another material property for radiation is the absorptivity. Absorptivity is Önder Kara. Okay. I have a student called Önder Karapakoğlu, so you are a different person. Okay, Önder Kara, please don't come to my class next time because only my students can come. Önder Karapakoğlu can come, but Önder Kara cannot come to my class. Okay, other people also. So who is Hacer? Who is Omar? I don't know who you are. Umut, who is Umut? I don't know. Okay, so make sure you are the correct person in my class. Absorptivity is the fraction of radiation energy incident on a surface that is absorbed by the surface. So when the radiation incident comes to a surface, the fraction which is absorbed by the surface is called absorptivity. Okay, and the remaining part is reflected. Alpha is between 0 and 1. A black body has an absorptivity value equal to 1. If it's a black body, 100% of incident radiation is absorbed. Okay. Kirchhoff's law says the emissivity and absorptivity of a surface at a given temperature and wavelength are equal to each other. Here, the rate of radiation absorbed is equal to absorptivity times incident radiation. Okay. Radiation heat transfer between the surfaces depend on the properties of the surface, their orientation relative to each other, and the interaction of the medium between the surfaces with radiation. For that reason, it is a complicated calculation, but here we consider a very simple case. Very simple. In the very simple case, there is a small body. This green one is a small body in a large room, completely surrounded by a large room. In this case, the radiation heat transfer between this small body and the surrounding surfaces is given by this equation. So the equation is epsilon emissivity of the small surface, surface area of the small surface. What is sigma? What is the name of the sigma? Sigma. What is it? So the name of the sigma is Stefan-Boltzmann constant. Ts is the surface temperature of the small body, and T surrounding is temperature of the surrounding surfaces. T surrounding here. T surroundings. Okay? Normally, there is heat transfer between this green small body and the surrounding surfaces. And it is equal to this. Epsilon sigma AS TS4 minus T surroundings 4. This is the radiation between this green small surface and the surrounding surfaces. Okay? This is how we calculate radiation in this simple case. Okay, the air temperature here, does it have any effect on the radiation, the rate of radiation between the green surface and the surrounding surfaces? Air temperature, does it have any effect? Is it affecting radiation, air, temperature of the air? Yes or no? Is it affecting radiation or not? Is it affecting radiation? Okay, no is the correct answer. Thank you, guys. So air temperature is not here, right? Which temperatures do we have? Ts, temperature of this surface, and T surrounding, temperature of surrounding surface. So radiation is between the surfaces. There is no air temperature. No air temperature here. Air temperature has no effect. Here there is also convection. Between this surface and the air, there is convection heat transfer. Between this surface and the surrounding surfaces, there is radiation heat transfer. Okay. Okay. Here, for example, if you want to write Q convection is equal to, what is the formula? Do you remember the formula? H AS TS minus, tell me what is left, what is it here? Tell me. So this is the convection heat transfer between this green surface and the air, because there is convection, right? Between this green surface and the air, there is convection heat transfer, and between this green surface and the surrounding surfaces, there is radiation heat transfer. Now, this is the radiation formula. What is the convection formula? H AS TS minus T infinity. That is correct. Okay. And the total heat transfer is Q. Total is equal to Q convection plus Q radiation. Okay. Q convection plus Q radiation. So there are two mechanisms of heat transfer here. From the green body surface to the air, there is convection heat transfer. Okay. So there is a convection heat transfer between the surface and the air. This is Q convection. And between the green surface and the surrounding surfaces, there is Q dot radiation. Okay. Is that understood? This is the radiation formula. This is the convection formula. Total heat transfer between the green surface and air and the surrounding surfaces is Q convection plus Q radiation. What's the direction of heat transfer? If, let's say Ts is equal to 40 degrees, T infinity is 20 degrees, T surrounding is 10 degrees. It could be like this, right? It could be like this. Then the rate of heat transfer is from surface to the air from surface to the surrounding surfaces. If the surrounding surfaces is 60 degrees, then radiation is from surroundings to the surface, but convection is from surface to the air. Okay, because heat transfer is always from high temperature to low temperature. Okay. Okay. Are there any questions? Are there any questions? Okay, good. Good. So the effect of Q total is Q convection plus Q radiation. This is Q convection, H convection, AS, TS minus T surrounding. This is the radiation. So sometimes we combine them together into one formula like this. We call it H combined. So effect of convection and radiation, effect of convection and radiation, effect of convection and radiation is combined into one equation. We call that H combined. H combined is equal to H convection plus H radiation. What is H radiation? H radiation is equal to this. This is your H radiation. This is how we combine conduction and convection and radiation together into one formula. This H combined has combined effect of convection and radiation. Sometimes we do that. Sometimes we do that. Here,